Hello, everyone. Can you guys hear me? You guys hear me?
Yeah, Professor, I can.
All right, great. All right, let's get started. Welcome. So today we are going to discuss recurrent neural networks. We're going to wrap up that topic today. So as you know, you had a homework assignment that was due. And so today we're going to go over it. Last week, we started looking at recurrent neural networks for images with MNIST. Okay, and then this week, we are going to look at recurrent neural networks for NLP. Right, so we'll
Professor, the assignment was due for just running the code or using different.
Say that again.
The assignment was due for just to run the code or to use different data set.
Well, I mean, it was really about, you could have ran that code and I'm sure it would work with that data. But it was really about making it your own. So I wasn't actually asking you to, I mean, if you running it with another data set just simply means finding another story, right? You can find, you know, hundreds of thousands of stories on the Gutenberg project, right? But nothing would really change about it. So what the whole point was to kind of look at it and clean it up as much as possible so that you have a better understanding of it. Because we're framing it as it's a different problem, correct?
So you mean to, actually, Professor, what happened is like, I was trying to do the same code using the test and the train data set, because your code is something related with the inbuilt library.
Can you speak up a little bit louder, Sumendra? I can barely hear you.
Yeah, so Professor, your code was something related with the inbuilt library, right, Professor? So
with the MNIST library, yes.
Yeah, so when I try to use it with the test and the train data set with the same MNIST data, I was like, I have a lot of issues on the main loop itself. So I get a lot of like troubles when I was trying to resolve it.
But you were trying to run text, correct? That's
not the text, Professor, because I guess you already have an example on your GitHub within text. I was trying to read.
Oh, you found mine? That's the solution to this, yeah. So I did it over the weekend.
Yeah, so my question is like, I was trying to do the same using the test and the train data set, but not using any library function, Professor. And the main
library functions for what?
Like for the data set.
For reading the data, you mean?
Yeah.
Yeah.
I was trying to understand the structure, like how we can feed it if we have.
Yeah. Well, I mean, that's the critical thing, right?
Yeah, and I get like a lot of error when I was trying to just load the data set. So I have certain questions, Professor, in the main loop itself.
Yeah. So let me go over, I'm going to go over the solution today. And as I said, I took that code and just modified it to be more consistent with the way we do things in the class. And so, hopefully that makes sense. The thing that's tricky here is understanding how the data is modeled. That's one of the challenges of this. But this is actually, we're kind of double dipping because the way that that's written, is also how, Ju, I can hear you, Ju. So the way that what was I saying? So the way that it's structured, I changed the code to kind of adapt it to the way we've been doing it in the course. this is a different problem. So as I said, the idea was to kind of look at different models, different ways of using RNNs. So this one would be a little bit different from the MNIST, you know, and so on. Okay?
Yes, Professor. But I think
Uh-huh.
just to feed the data
Yeah?
in the main loop and to
Can you
run.
speak up, Sumendra? I can barely hear you.
Can you hear me right now,
Yeah,
Professor?
I can hear you. Yeah.
Okay. So uh, the main problem that I encountered was like the main loop when we try to feed the data uh, to our training session.
Mhm.
So that part was like I couldn't still understand, Professor, like
Right. No, that, you know, that's fine, Sumendra. That's
because I was able to run
the
your
hardest
code.
part.
I was
Huh?
able to run your code on like TensorFlow 2.0 because we have to make certain changes, and it was working perfectly fine. But when I tried to do it with the train and the test data set, then
First of all, what is the train and the test data set? That's where I'm a little bit confused because
the CSV file, Professor.
this is a different problem, okay? This is you know, this is not, you're learning from, I think let me just go over it honestly.
Mhm.
I think, you know, this is a different problem from what we've done because it's natural language processing, RNNs. Kind of have to understand how you go from text to feature vectors and all of that. Okay, Sumendra?
Yeah, Professor. But I
Yes,
guess
sir.
this is also used for image also, right, Professor? There are certain examples.
Right. I mean, we did. I mean, last week we applied RNNs to images. I mean, it can work if you. So any model can work for anything if you know how to apply it. That's the whole point. So it's not like it's a cookie cutter kind of thing, and oh, I'm going to apply that. No, you always have to figure out how to feed your data into your models. Okay,
Yeah,
that's the challenge with all of this. You know, hopefully, but you know, by this point in the course, you've seen that the algorithms rarely change.
yeah. The main thing is just
Lectures, you
feed the
tweak them a
data.
little, but it's about fitting your data into these models. You see that?
Yeah, that's the main challenge. I like
It's the
always.
main challenge. I agree with you. Don't feel discouraged if you were not able to, you know, understand it. It's challenging. But what's great about this example is that Word2Vec, which is distributed vector representations, also takes a similar approach. And remember, Word2Vec is completely unsupervised. And so, and this is technically unsupervised. We're just using the text. There's no labels per se. You just create something that will be a label, the thing that you're trying to predict. All right?
Mhm.
All right, so let's take a look at it. You know, there's quite a bit that we need to talk about for this. So for those of you, as I was saying to Sumendra, for those of you that just came in, just a few reminders. This is basically our last week of new lectures, of new content. Next week, as you know, is our presentations. So next Tuesday from 12 to 3, you guys will do your presentations, okay, of your term project. So don't forget that. We're going to meet here on Zoom, and you'll be sharing your screens and doing your demos, okay?
Okay.
All right. That will be the plan. So please do not forget that. And then the week after that, we'll have our final exam. So you can just go ahead on online, you know, look for a PNW final exam schedule, and you look for Tuesday at 12, and then that'll tell you when the exam's going to be, probably around that same time. Okay, it'll be an online exam like the midterm. Okay, I think I've graded everything at this point. Everything is posted. And so now what we're going to do is we're going to solve this RNN problem. Okay, so we're going to solve it. All right, so let's go ahead and kind of get started with this. So there's a few things I want to do. So you guys should be seeing my virtual machine, correct? Guys, is that what you're seeing?
Yeah,
Yes, Professor.
Okay, great.
you can see.
All right, so let's start with the problem, just kind of remind ourselves of it. I posted the code already, and so we're gonna take a look at the code, and then we're gonna run it on the virtual machine. But let's kind of go over the problem first. Okay, so I'm going to share. Showing. All right, so now you should be looking at the website, okay? So, LSTM by example using TensorFlow. So the idea here is that we have an NLP problem. Okay, we have a natural language processing problem, and we want to solve it with the recurrent neural networks. Okay, so we've talked about the definitions already. We went over that last week, all the details of that. And so now, basically we have some text. You can pick any kind of text that you want. I just ended up using this text, but you could use, if you like Star Wars, you can pick all the scripts from Star Wars, put them there. Or if you like, let's say Star Trek, which probably has a lot of scripts because of all the TV shows, put those in there. And at the end of the day, what happens is that you're creating a program, an AI. This is technically an AI, right? So this is, a very, not very intelligent AI, but this is technically an AI, a chatbot, that kind of thing. So you're teaching it to speak the language of Star Wars or Star Trek or these fables from Aesop's, right? So you're teaching it the sequence of words that should be, generated. So the idea is that it's going to generate stories, right? Stories. Now, are the stories grammatical? No. It doesn't learn grammar. It only learns, by frequencies of words. If I see 3 words, what's the most likely next word? That's really what it's learning. And then based on that, it's going to start creating stories. So you will notice that the stories, statistically speaking, if you look at the words, they will have the same occurrences as the actual stories of the author. The only problem is there won't be grammar in there. There's, we as human beings, we probably have an RNN of some type, but there's some additional mechanisms up there, that, maybe a set of grammar rules and things like that, that govern how, and also imagination, all kinds of things that allows us to write stories, whereas this program doesn't. It only by frequency, guesses the next possible word. All right, so that's the scenario, okay? And so now we need to frame this problem. So if you can see here in this example, the example shows that you basically have a vocabulary of 112 unique symbols. So that's equivalent to saying that you have 112 words in your dictionary that you're trying to predict, okay? And so here's the model as we looked at it. So in the model, you have 3 inputs, all right? And the inputs is very interesting how this is done. The inputs could be one-hot encoded, but they're actually not. They're just integers. But they're integers that represent the one-hot encodedness. Okay, and we will see that. All right, and then you feed that sequence of words. So you feed like had, a, general. Those are the inputs. Obviously, you don't feed the words. You feed the integer of, or let's say the index of the integer of the one-hot encoded element that would have a 1 in that vector. All right, and then you have a hidden layers of the RNN using LSTM cells, and then from there you predict a word. So you're going to predict the word, that should be there. So for instance, the word that should be there, the fourth word is council, but the RNN might predict the word prediction. Okay? Is this clear for everyone? Any questions? All right, no questions. So then what we have to do is we have to use these functions, okay? Build data set. And so in this function actually that you see there is also at the heart of distributed vector representations and word2vec. Word2vec uses pretty much the exact same approach. And so actually, once we, and what I like about this example is that this is less complicated than the word2vec code. So we're actually understanding a little piece of word2vec now of how the text is converted into vectors for training. So again, notice that in your model, this will be a vector, a one-hot encoded vector of the dictionary, the words, and this also is the index, which basically would represent the index of the one-hot encoded vector of the words. Okay, the corresponding index for the given word. So for instance, here, comma is 0, the is 1, council is 37, spoke is 111, and so on. And those indices are assigned by frequency, okay? And that's what we will see here, but we'll talk about that more once I look at the code, okay? So we have that. And so here you can see when the algorithm is doing really well, it might predict, given that it should be 37, it'll predict 37 because it'll predict the highest probability for this vector. And then here's the RNN. If you notice, this RNN inference function is exactly the same as what we had in our previous example last week with MNIST, okay? And so, we're just gonna tweak it a little bit and, get our results. And then we have the parameters, so I'll talk about it. What I did is I took their code and I just changed it to fit more the way that I've been writing the code in the class. And so you'll see that in my example. I should say a lot of it in this code, when you deal with NLP, is not, it's a lot of like magical tricks that you do in programming. So it's your ability in programming to convert things. So it's not really about the deep learning per se. It's more about just converting the data to the formats that you need to use. And so hopefully that will make sense. And I believe it's important, okay, that we understand this part. Because if you ever use NLP for anything, text, natural language processing, or similar approaches, it's good to understand these aspects. All right, so let's go ahead. And then at the end, this is what you get, okay? So you end up predicting the, you know how to print out like accuracies and loss functions. But at the end of the day, you give it this means we, and it should be should, and it predicts should. So here, it's really good. So, I ended up running my code like 10,000 times, and I think I will run it 10,000 times here, just because I want to see the part where it generates a story. However, keep in mind that when you train it for only 10,000 iterations, it's not learning as much. So you have to give it more, probably 100,000 or a little bit more. Okay?
Yeah.
All right, great. All right, and so that's the, these are the core functions. So probably you read through all of that. All right, so I think that's what I wanted to illustrate of that. So now let's go to GitHub, and I just want to show you the code and then kind of give you an overview of it. And then we're going to get into we have a class today. We're going to get into the meat of this. So as I was saying, we are out of time, unfortunately. We have 2 topics, okay, guys? We have 2 topics that we had left, which was word2vec and reinforcement learning. So for Word2Vec, what I did is, if you notice here, are you guys seeing my my GitHub? Can you guys see my GitHub?
Yeah, Professor.
Yeah.
Okay, great. So what I did for Word2Vec is I'm hoping I'll have a few minutes at the end of class today to go over Word2Vec. But if I don't, I've posted this, a Word2Vec folder, and you can see I have you know, a text file there with instructions. So you can download the data. It's actually very interesting. This is all the what is the COVID-19 thing, you know, this thing that's going on. It's all the research papers from, you know, that basically all the research papers that have been written in English related to COVID-19 and those types of things. So if you guys are interested in a little bit of research in that area, you know, you can go ahead. So here I wrote, this uses COVID-19 research paper, about 10,000 full articles and 40,000 abstracts. You can download it. I put the link here. I posted it on my server. It's in JSON, okay? It's in JSON. So the issue here is that you would have to read it from JSON and convert it to actual normal text. You can, I mean, the code works leaving it as JSON, but you don't want that JSON stuff in there. Okay, so, but you know, the JSON is helpful because it's like annotated in some way, and so you can remember this would be a totally unsupervised problem, right? When you use Word2Vec, is 100% unsupervised, like a clustering thing. So you can download the data set there, and then you can run my code. I wrote it, you know, actually Mitch Burke, a student in our class, he got the code and modified it, kind of fit it to the way that we write in the class. He will do a presentation on this topic, I believe, on Tuesday. I don't know if he's online right now, but so Mitch, this is Mitch's code for his presentation, and he will obviously go over it. So, you know, that's kind of how that's going to be helpful. You know, you guys can, but if you want to beforehand run it on your own, you can. What's great about this is you're going to run the code, and all you have to do is put these files in a folder, put the code, you know, kind of outside that folder, run the code. It'll read all the files that are COVID-19 related, and then it'll apply Word2Vec to them. Okay, and it's not really that large, amazingly. It's not, because it, you know, 100,000, 40,000 abstracts are just short, and then 10,000 articles. And articles usually are like 8, 10 pages long anyway. It's all text, I think UTF-8, and it'll perform Word2Vec. And if you, you know, just really quickly, Word2Vec basically creates a vector space of a set of dimensions that you give it, let's say 200. And then every point in that vector space is a word. It's a word in that corpus. Okay, it obviously selects the most frequent words. And that approach is very similar to what we're gonna do with RNNs. So what I'm going to explain today about RNNs and how we go from the text to these dictionary and reverse dictionary, well, that's exactly what Word2Vec also does. Word2Vec has a little bit more because it's different, but there's similarities there. So if you understand a lot of the RNN stuff today, that will considerably help you to understand Word2Vec. All right, so that creates a vector space of, let's say, I think in the code we're using, Mitch wrote 128 dimensions. So you set those, and those vectors are semantic vectors. I think I've talked about this a little bit. So they have actual meaning. We don't know what the meaning is, but it is some meaning. So maybe in the context of COVID-19, it might be like vaccines and, you know, illness and stuff like that. All right, so once the vector space is created, you know, usually you print out a little text file, and the little text file the text file will have every word and its vector representation, which means it'll be at size 128 or 200, whatever you decide to use. This code also introduces something called TensorBoard. And TensorBoard is a really nice way of visualizing your data. So what you have to do is you're gonna run the code. And once you run, after the code finishes, on the terminal, run this, okay? Run that command. When you run TensorBoard, it'll give you on the same command line, it'll give you a port number, okay? So what it does is TensorBoard creates like a web app, you know, running Apache. And so what you have to do then is you will go to your browser and type localhost : number that it gave you. Okay? So you can see for it, yeah, you wrote an example in browser, URL box type, something like this. Assuming it gave you port 1000, it'll be a port close to 1006. It might be that one. And then once you do that, something very nice will be generated on your screen, like a little dashboard. So that's the TensorBoard. And so in the TensorBoard site, you can select, there's gonna be several drop downs on the upper right-hand corner. There will be a drop down. You can select Projector. And in Projector now, you will be able to see that space. So remember that we as humans can't visualize spaces that have 128 dimensions or 200. So for those of you that remember the machine learning course, we talked about something called singular value decomposition. There are other techniques like PCA and TSNE. And so it uses one of those techniques to compress the data from a vector space of 128 to 3 dimensions. So you basically will be able to see a 3-dimensional vector space that will have all the words in there. And then that should be nice. So after that, you know, you can play with it. As I said, Mitch is gonna present that on Tuesday anyway, so you'll get more information on that. But at least, you know, in the course, I was able to give you the Word2Vec code, give you some text files, and now you know how to use it. You know, we may not have enough time to go over all the details of how Word2Vec works. Now, I should say that that's actually fine. Word2Vec is one of those algorithms that, in my experience, I always use as a black box. I rarely, if ever, change anything. There's no need to change the architecture, you know, because it's actually not even a deep neural network. Word2Vec is just a neural net. It's got an input and output and a hidden layer in between, usually. And so there's very little that you have to change as far as the architecture. So usually I always just use the code as is. So the code as is, I just use that. You know, sometimes you might have to change, like the problem, like if your files are JSON, you know, I leave that to you guys to fix. I know Mitch fixed that somehow, and he might actually, if he's listening to the video, might send me a link with the file he's using without the JSON, and that might actually be even more help, be even of greater good. It's not a homework assignment. It's just me trying to give you Word2Vec given the limited amount of time that we have left. Was all of that clear?
Yeah, it's clear.
All right, excellent. All right, so there you go. So that's Word2Vec. And click on the folder. You can see the code here, Word2Vec. Also, I should say I pretty much explain all of this in great detail in my book. So if you have a copy of my book, just find, I think it's chapter 5, and you'll find Word2Vec in there. Every line of code here is explained, okay? And it shows everything, on how everything works. All of that, all of it is very detailed there. All right, so that being said, so I'm done, kind of with Word2Vec as far as that. So let's go now to RNNs. Go back to RNNs. And, you know, like I kind of like this idea of doing RNNs with NLP and then that leading into Word2Vec because, as I said, there's similarities here. You know, Word2Vec uses that dictionary and the reverse dictionary just exactly like RNN uses it. And so once you understand this, you've understood a part of Word2Vec. All right, so let's go to RNNs. And if you notice, I created a folder called NLP. In NLP, so this is basically the solution to your homework assignment for today. Okay, this is what I was looking for you to do. If you notice, I put two text files in here. I just took the text files that they were using. And then this is the code. I took their code and modified it. Okay, so I wanted it to be a little bit more consistent with my, you know, the way I do things with modular functions, you know, kept all the structures. I wanted to, as I said, run like Star Wars, Star Trek, or something that would have a unique set of words like that, you know. Lord of the Rings would be another one, maybe Shakespeare. So you guys can do that. You know, I strongly recommend that you play with that and look at the stories. Remember, you have to train it a long time. Otherwise, if you don't train it a long time, you'll see that it pretty much creates the same sequences of words. Okay, and so you wanna actually try a few more things. All right, so let's take a look at the text first. And you can see it's just a string, a very long string of text, right? You know, it's grammatical. So long ago, the mice had a general council to consider what measures they could take to outfit their common enemy, the cat, right? So these are, you know, children's stories. So in NLP, I always like to work with children's stories. You know, they're very grammatical. They're very whimsical, and the semantics, you know, one thing about what I like about this is that the semantics of these are different, right? You know, mice here have a general counsel, which, you know, depending on how much you like cats, that may or may not be true. So, you know, but it's interesting. It represents a semantic challenge, first of all. All right, so now, so that's the input file. Notice it's just, you know, one story. It could be really, really long. Notice this one is not very long, which means that your vocabulary is very small. Obviously, the bigger it is, you know, like if we were using all of COVID-19 or whatever, you know, you can do that too. You can fit all the articles into one file. I think that's what Mitch actually did. Or you can find other ways of reading it. It really doesn't matter. At the end of the day, the input is a very giant string. All right, so now that we've talked about the text, let's look at the code. All right, so this is the code. I've modified it, as I said, to kind of fit our structure. So I really, you know, I'm going to talk about that first, the structure, and then we're going to have to get into all the details. And please stop me at any time if you have any questions, okay? All right, so if you notice, the first thing I did is, you know, I kind of took like MNIST, the MNIST code that I showed you last week, and then I took their code and I integrated both in a way that it would look like what you've been learning all semester. So my goal for the semester has been for you to always have this template that you have the inference function, the loss function, the train test, you have the main loop, and then, you know, placeholders and things like that. And then we change some things about that, but there's always this template that we follow. And, you know, I've usually been successful in doing that, you know, and so that's great. All right, so you can see here, these are the libraries. As you can see, it's pretty much the same libraries that we've been using. Oops. All right, then I have some parameters there to remove warnings, printing numpy arrays. That's just, you know, you can ignore that. And then I have the main parameters. So you can see here, I have a learning rate of 0.001, Number of epochs is 50,000. For today's demo in the class, I'm going to have to reduce that to 10,000 just because it takes too long. But I encourage you to run this at home, you know, with more iterations, just to see how the story, how the algorithm actually does, how your AI, your chatbot actually does. Initially, the vocabulary size is 0 because this has to be updated after you read the story and you do the calculation. So initially it's 0, but it'll be updated below. Number of inputs is 3, okay? And that, you know, that's important because remember that we are feeding 3 cells basically, right? So 3 pieces of information into our RNN. So an input, which is basically for the placeholder X, right, is the number of features. So it's like we're saying we only have 3 features. Notice here that this is not being one-hot encoded, right? This is, you know, so it's gonna be the index values, but they're not gonna be one-hot encoded vectors. So n input equal 3. And then n hidden is going to be, you know how in the RNN you have inputs and outputs, and in between you have the hidden layers. Well, the hidden layers are going to be of size 512. Okay. Are there any questions, guys, so far?
Yeah, Professor, with the n input, so
Go ahead.
basically we define the features on our own here, so, or it's based on the data set?
You define how many words you're going to give it. That's what you define. So for instance, could I do this to define 5 words in a sequence? Sure. 8? Sure. How about 1,375? Sure. But how good is it gonna be if it has to predict a sequence of 1,735, you think? Not very good, right? It's kind of the argument there. There's no way for me to answer this except to say, so, you know, NLP, natural language processing, that could be a course, right? So we could spend an entire semester or 2 on it. One of the things that you learn in NLP when you're dealing with sequences is what is called bigrams, trigrams, and n-grams. And what that means is that, unfortunately, I can't write on here, but let me actually switch to the whiteboard. All right, so can you see my whiteboard?
Yeah, Professor, yeah.
Okay, so what we're doing is we have 3 inputs that feed into these hidden layers, right? Hidden layer, hidden layer. And then that predicts an output. Okay, that's kind of, we could also predict more outputs here, but if you notice, we're just ignoring these. And we don't care about them. We just want that one, which would be in essence, it would be the 4th word that goes there in the story, you know, based on, you know, the car is, what would this word be for you?
It would be fast, slow, good.
The car is fast?
Yeah. Okay,
that could be a word. That's true. Going, right? Fast, you know, and so on. Exactly. So that's what you're doing. That's what your goal is here, right? To predict that. And so we are building a model like this. And so what this is showing you is how to feed that into a recurrent neural network. When you have an NLP, this is a classic problem. This is like one of the main 3 pillars of NLP, right? These sequences. And so this actually has a name. It's called n-grams. Usually you have bigrams, and it's just 2. Grams would be sequences of 3. So this is a trigram type of thing. And then n-grams would be more than 3, right? Anything beyond that. The problem with that, with trigrams and n-grams and so on, is that the occurrence of phrases, you know, the car is going, the frequency that that occurs 3 times in a text is very low. You see that? But the frequency that the car occurs, just that bigram, is more likely. You see that? So bigrams have more occurrence in a text than trigrams. You see that? And 4grams and so on. So you decide what you want to use. So in general, people in NLP prefer shorter things. Does this make sense?
Yeah, Professor. Okay.
Yeah, and in fact, even trigrams are not used as, you know, the standard is always to use bigrams. Because with a bigram, which is what, what this RNN kind of does, you learn from here, right? And then once you're here, then you're going to learn the next one. You don't have to worry about, if I'm here, what's going to be that one, right? You only worry about this one. You see that?
Mm-hmm.
Samendra?
Yes, Professor, yeah.
Yeah. So this is a choice that you make, okay? Predicting 3, but in general, what I'm trying to say is the shorter, the better. The shorter, the better. Because all of this is based on frequencies, and it's based on the occurrence of a word. How you'll see that we do basically a frequency estimation of the most frequent words, and so you might have one particular word in there that occurs very rarely, and so that hinders your ability to build very long sequences. Did that answer your question?
Yeah, Professor.
Okay, great. All right, so anyway, so our goal then is to build something like this, okay? This is the architecture that we're trying to build. Okay? We want 3. And we want to be able to predict that one. This is the model. And so like I said, what I'm trying to show you here also with this example is that the key to understanding these algorithms, hopefully by now, you understand that the code changes very little. The architectures change somewhat, but it's always about fitting your data into the problem. And so honestly, in my opinion, the best way to understand these algorithms is applying them to lots of different things. Okay, so you want to, so far we've applied this to images. And in RNN, we tried to apply it to images. Now we're applying it to text. Maybe you want to apply it to finance. You could also apply it to these models that predict this prediction of the pandemic. It predicts the number of deaths per day. So imagine, you predict some number here and then a number here and so on. So it can be used for a lot of things. Okay. So that's the idea. All right, so let's go back to our code. Go back to our code here. All right, so I just want to go over the code first, just kind of, high level, and then we're going to get into the details. So we talked about the parameters, right? And then this is the story. You can see here, that's the training data. Then we have this function, read data. That function is the function that will take this data, read it in. We do that by calling it here, right? And then once we've read it, because you can see, we called training data here. Then we have this other function called build dataset, and build dataset is this one which calls training data, the data that we just read into memory. And the output of that is something called the dictionary and the reverse dictionary. Those are the 2 little tricks. And like I said, whenever you're using NLP, you pretty much take this approach, right? And problems with text take this approach usually. There's a few tweaks here and there, but in general, they create these dictionaries and reverse dictionaries because that's how you create your feature vectors. Notice here, we calculate the vocabulary size by calculating the length of dictionary. And if you look, vocab size is one of the main parameters here. Okay, the one that was initialized at 0. Now it's actually getting the value of the length of the dictionary. Then over here, you just have the standard precision print stats metrics function. That hasn't changed. Number of epochs, that hasn't changed. And then here is our inference function. All right, so RNN NLP is your inference function, right? It's pretty much exactly what we have done in what we did last week with the MNIST data set. So we did RNN MNIST back that week, right? This one is very similar. I tried to make it as much as I could. Notice that the transpose is missing here because the data that we're dealing doesn't require that transpose, right? It doesn't require us to make that change, but everything else is pretty consistent. Then after that, look at the loss. Is exactly the same loss we've used, softmax cross entropy with logics. The training is exactly the same, except that instead of using the atom optimizer for this type of problem, it has been proven empirically that this is a better optimizer. Okay, we're not going to get into the details of how this optimizer is different. I'm pretty much, just pretty much whenever you're dealing with these kinds of problems, you could use this. The evaluate function, that's the same function that we've used for accuracy, so that doesn't change. Remember that we're going to have, whenever we're doing, let me go back to the whiteboard over here. Are you guys seeing my whiteboard again?
Yeah, Professor.
Yeah. So whenever we're doing this, so we have a story. The cat is sleeping, right? And then we have our model. One of the tricks is, let's say we do the cat is, right? So the hidden Markov model, or sorry, not hidden Markov, sorry, the RNN wants to predict this word. It wants to predict that the word is sleeping. So there's something in the code called, it's an index. I think it's called offset. But it's really, actually, I debated this. I think the word should have been index. And what it does is it's keeping track of its current position in the story, right? So it's saying, I am there. You see that? And so for instance, you're there, so you grab these 3 words, you feed them into the RNN. The RNN has already been trained. What does it predict here? It predicts the word, let's say, sleeping. When you did this in the test, this is the test phase, right? So after training, you're doing testing. So in the test phase, you have an index and you're iterating through the entire story, word by word, a cat is, and so on. You feed it into the network and it's going to predict the word sleeping. Well, the offset knows that it gave this, this, and this as inputs. Therefore, this one is what? The output. You guys see that? So in terms of if you want to think of this as a supervised learning problem, this is your input vector, this is the output vector, right? And the input vector is going to say the cat is. It goes into the model, and the model then predicts which word it is from. Let's say you have 100 to 200 words, so it's going to say, boom, that one, 175. Well, as it turns out, you go to the dictionary, look up 175, and guess which word it is? Sleeping. You see that? And then, because you just did this, you actually know that the label is sleeping. Let's say we have it here, sleeping. And so what happens in the test set is that you can compare the predicted, so this is pred, and this is label. So you can compare both of these and say if it was correct or not, because it's like a classifier, right? So if it's sleeping, and I'm going to make a vector that's a little bit smaller. Let's say that that's sleeping. So that's the label. This is pred. So then if it predicts this, it predicted the right word, sleeping. However, if instead it predicts that, that's another word. And so therefore, they do not match. Does this make sense, guys? That's how you do the testing phase. Is this clear?
Yeah.
All right, great. Sounds like, are there no questions? Is all of this, everyone's very quiet. So it seems like you all understood it. It's good. Okay, well, that's good. All right, so let's go back to I'm going to share now my GitHub again. All right, so where you guys are seeing, you should be seeing my GitHub now. All right, so as I was saying, we look at the functions. So the main function that will change is RNN NLP. Okay, that's the function that's going to change from, not much, but it's going to change from problem to problem. The loss is the same. Training just has this one little change from atom optimizer to yet another type of optimizer that has been empirically shown to be best at this. Evaluate is just the accuracy function that we've been using, so that doesn't change. Notice here, this is our placeholders, right? So this is XTF and YTF. First of all, look at this one here. So the size is none by vocab size. So if we have a vector, if we have a vocabulary of 200 words, then that's going to be 0 by 200, right? It's going to be the one-hot encoded vectors, where 1 is only for that word that's being represented there, and the other ones are going to be value 0. Notice on the other end, the XTF is going to be none, in case we have several batches. In this problem, we didn't have batches. So that's one of the things that simplified the problem, is that every iteration in the training, we didn't give it a batch of sequences, we only gave it 1. All right, and so this is going to be none by 3, which is the n input, because there are 3 words. And what we give it is the index. We don't give it the one-hot encoded vectors. And then we give it a 1, okay? A 1. So ultimately, this tensor would be 1 by 3 by 1, okay? And just remember that, that this is how we're feeding the data into the RNN. Okay, once we have the placeholders, then, it's just the same thing as we've done before every time. We call the core functions. So we call RNN, we give it XTF. That's just, what's going to be in there is our sequences, right? This is going to be the sequences of words. And remember, it's going to be like if the word the is 3, car is 17, is 5, then you're going to feed it 3, 17, and 5. That's XTF. That predicts your inference output, right? You also have your loss, which is going to be the loss between the output and the real. So the actual word that you take from the story and the word that it predicts. The training, which is just minimizing cost. And then your evaluate function over here, which compares the predicted to the actual. Once you do that, notice over here, TF argmax output 1. This is the same function that I've always had in my code for taking something that is a 1. Whenever we had the outputs, remember, It's always one hot encoded. But to predict the word, we need to take it from the one hot encoded back to the index, right? So if I go back again to GitHub over here, sorry, to the whiteboard, you know, that function, it's whenever we have this, right? Let's say this is 200. So we convert it into the non-one hot encoded. So this is 0, 1, 2, 3, 4, 5. So the argmax gives you the index of the highest value, right? So in this case, 5, because that's the predicted word. And then in the dictionary, we're going to look it up. 5, and that's going to be equal to, let's say, car. And so we found our word. And that's really how it works. Remember that in Python, dictionaries are really efficient, and so it makes sense to use them. Okay? All right, so you guys saw my whiteboard, correct? This is what you're seeing?
Yes, Professor.
All right, great. So let's go back to the GitHub. All right, so that's what this does, right? So it just, you can see here I wrote output no one hot. So the one hot is removed. Instead, you have the predicted word ID that can be looked up in the dictionary. After that, notice I have, you know, this was a little bit different in their code. That's why I said I modified their, you know, their code to fit into the way, the structure of how I write the code. I just think that, you know, I firmly believe that having these sections just makes this a lot more predictable than writing spaghetti code. So anyway, so after this, we initialize everything. So initialize all variables, the session, run, so on. There's a step here, step equals 0, and that's just really, you know, to keep track of the number of steps. That's not, there's nothing to it. And then finally, look, there's 2 sections in here, right? So there's this section, and then this is the main loop. So the main loop is actually this, our usual main loop in deep learning. This is an add-on that what I, you know, when I was working with this code initially, I just commented all of this out. Okay, this section is for generating a story. So once you train the model, you give it 3 inputs, and then from there, it's going to generate a story of however, I think I wrote like 64 words. Yeah, 64. You can see that there. So it generates basically a 64-word paragraph based on what it learned. But for now, so this is, you can see here, this is after training, and this generates a short story using the trained RNN. So for now, we can completely ignore this, and then we can come back to it later. So really then, that being said, all that's left for us to understand is this, right? Understanding the main loop, and also understanding, I think, these functions, build data set and read data, which are pretty straightforward. And then the inference function, we'll definitely go over that again. But really then, this is the main loop, okay? Now, for now, I'm just gonna go over the main loop kind of in a high level because we need to understand the dictionary and the reverse dictionary before we actually understand what's going on here, okay? And as I said, this is very important because this is the foundation for a lot of NLP things with deep learning, including word2vec as well, which is distributed vector representation. So I really want you to understand. And also, like I said, if you know, if you look at in my book, if you have it, I've painstakingly gone over the word2vec code line by line and explain every single thing as well in there. All right, so here is the main loop. Let's just do an overview of it first. All right, so, and give me a sec to get some coffee. Give me a sec. All right, I'm back. Sorry, it's just my throat gets, from talking. All right, so we're talking about the main loop here, the last part of the RNN. There's one thing that's extremely important to understand. So I'm going to start with that. This little variable called offset is, as I said, I kept it as they had it in the code, but really I would like to call this index, because what this does is it keeps track of where you are in the story. You know how you guys, I'm sure you do this, whenever you read a book or study, you're reading a book, you have a red pen or whatever, and you're reading, and then you mark a little line at the beginning of a paragraph, at the end of a sentence, wherever you are, you mark a little thing, and so you know where to start again. And that's what this does. This is keeping track of the current position where you are in the story. Keep in mind, this is moving, this might be moving one word at a time, but it's looking at sequences of 3 to predict the 4th element. Okay, so that's extremely important to understand. Okay, so that's extremely important to understand. Okay, so let's see. So use offset, and this is sometimes called a sliding window. Okay, a lot of people, in Word2Vec also, they're gonna call it a sliding window, or a buffer, or the window size. Lots of things. This has existed for a long time. It's not like this is new at all. I mean, 10 years ago, before deep learning, I was using something like this already. And so it's a very common thing, right? So to slide and look at the words, as I said, because of this idea of bigrams and trigrams. You don't want to look at sequences that are too long. Anyway, so you use an offset to slide the window across the document, right? And you can remember, you can think of the document as a string. So literally any document that you have is just a very long string that just continues going straight, right? So don't imagine, there's no enters or anything like that. We're gonna get rid of that. We're just gonna make it into a string from beginning to end. And so you can just iterate through it like an extremely long train car, right? Imagine that's what it is. And every car in that train car or train, it has an index, so you're kind of iterating through it. Every iteration offset is incremented. Okay, you're just moving through it. It is the index that tracks the current position in the document. Now notice here, initially, n input is 3, right? So remember, n input is 3, and it's always 3. Okay, and then you add 1 because that's going to be the 4th word that's predicted, right? Or it's going to be the word after it's predicted. But what's important here is that it creates a little buffer, right? So if I go back to the whiteboard, right? So the offset, you have the car is going fast, right? And so you are, your offset fast today at, right? So if I'm here, this is where offset is, right? Then I know really that I want 0, 1, 2. That's the 3 words that are going to be in my RNN, and I'm predicting that one. So that's, that's why it's going to be offset, which is 3, and then plus 1. So it gives you really a window size, a buffer, right? So it's like I'm centered there, but I'm looking at that one, and that one. And we just keep, this is just the simplest thing that you can do. With Word2Vec, think right? So with word Tyvek, actually sometimes you have to look at not just the words going forward, but also the words, you know, 2 words to the left, 2 words to the right. So it's the same idea. It's just that your windows could be different. Okay, so just keep that in mind. But for our problem, it is for my problem, it's just, you know, the car is going fast. Okay, so offset is there, right? And then end offset then would be 3 plus 1, so it's gonna indicate like that's the end of offset, like that. And that gives you then what you're focusing on in your data. Okay, that's a very important parameter because it really governs what data you're reading in. Are there any questions about any of that?
So Professor,
Yeah, go ahead, Sumendra.
the offset will keep on feeding the word, and then the slider will keep on moving, and it just predict, right? And
That's right.
The prediction is like based on like how good the algorithm we use.
That's right. So in the training, what you just described is the training. So initially the model hasn't learned, right? So what you do is you find a word with the offset, you look at the next 3 words, those are the 3 inputs to the training, and the 4th one would be the label, right?
Yes, Professor.
Make sense?
Mm-hmm.
Yeah, so that's how it works. And then you iterate again, and now you've moved another word, and then that word plus the next 2 are the training. The 4th one is the label, and you keep just doing that, doing that, doing that. So eventually you learn that whenever I see sequences like this, you know, I get that output. All right. So let's keep going. Okay, so this is important. So you have now offset. Notice that it has this strange notion here of picking a random number from 0 to 4. And what that means is, can anyone tell me what you think this means actually? Notice that's only done once, right? It's only done once outside of the loop. So why do you think it does that? Because the starting point of the sequence is important, right? So you don't always start with, you know, the sequence the car is, the car is, the car is. Sometimes you can start with sequences like car is going, car is going, car is going. Or the next time you start with is going fast, is going fast, is going fast. So it picks, you know, it's just to try different, you know, a little bit of variation. So you don't always end up with the same starting point. Okay, so that's kind of what that does. Obviously, if you had more text, if you have a lot more text, you would not have to do this. This is just, you know, it's not so necessary, I think. Because at the end of the day, it's only used once, right? It's only used once in the thing there. All right, so now, and then it is used here, so but I have to talk about that. All right, then end offset, as I said, is going to be 3 plus 1. So it's just the size of the window. The next step is now that we understand those 2 very critical things, let's look at the loop. All right, so our main loop is just, you know, a while loop until we have reached number of epochs, which in this case, I would recommend somewhere around between 50,000 and 100,000 epochs. As I said, you'll notice that when I do 10,000, it takes a while and it doesn't really learn very well to create the sentences. So more iterations is probably good. We also don't have that much in terms of text. So we just keep feeding the same data over and over and over and over. All right, so obviously when, you might have this question of what happens when we get to the end of the story, right? So we're in a document, we start at position 1, we're repeating this training process a million times. Obviously, we're gonna get to the end of the story. What do we do then? So what we should do is we're gonna reset, we should reset the offset, right? And go back to the beginning. And that's kind of what happens here. If you notice, we have this statement, right? Offset equals random int from 0 to 4. So again, we reset it to 0, we reset it to wherever, and so we just end up going back to the beginning of the story. So I wrote there, reset to beginning of document. Now, when do you do that? You do that when the offset, which is the index, is greater than the length of training data. So training data is your story, right? So let's say your story has 1,000 words, not unique words, but just, the car is going really fast. So that whole story has 1,000 words. So when you get to 1,000, which is the length of training data, minus end offset, which is 4, that means that you're at the last trigram for predicting. You see that? So you're going to be at just before the end. You're going to be 4 words just before the end. And so that at that point, if you did one more, you're not going to have words anymore and your program will crash. And so that's why, you check if offset, the index position, it's greater than that, then you reset the index and you start over again. Does this make sense? Yeah?
Yeah, Professor.
Yeah, all right, great. So now comes the last part. So if you notice, I divided it into 2 sections. This is train, just like every time we do a while loop, there's the session run. Notice session run, and then we call train up right there. And so, but because of the nature of this data, we have to do this, right? We have to do all of that just to get our training and our testing data. This is the part that, we have to look at the functions, the dictionary, reverse dictionary, and then we're going to come back to this part. Once you do the training, then you are ready to, you can see here. Actually, when you do the training, you're also predicting a word, if you notice. I should say that. So here, we run train up, but notice we also run output. So there's no need for it. You could have it. There's no reason why you can't have a second session run just for output. But if you notice in this code, you just run it here at the same time. Maybe at the beginning, this will be gibberish, but later on it starts to make sense. It should start to make sense. And so in this session run, we run both train up and output. All right, so after we run this, then now we also have the predicted word. We have the word in one hot encoded measure, but also predicted. You see that? And so now you can see that in this section, we just want to print out the words and see how it's doing. So the first one, because we have the offset, we know where we are in the story. So we're able to then figure out the test sequence. And here we are actually able to predict the actual word after the sequence. And this one is going to be the predicted. So this pred word, which is an index, right, from the reverse dictionary would give us the pred. So at the end of the day, we can print out what step we're in, the test sequence, the car is, the actual word going, and then the predicted word, which could be something else. Initially, it probably will. So the car is, and then here it says bird, or something, right? So that's what's happening in this code, if that makes sense. Finally, we we take the step size here, step plus 1, and that's just incrementing the number of epochs. And notice here something interesting. The offset obviously has to be incremented. Now, could we have incremented the offset by 1? Sure. But notice that here it is incrementing the offset by n input plus 1. So really, what would you conclude about that? You could conclude that it is ignoring, it's not repeating, or it's not double dipping or overlapping the sequences. Let me put it that way. And so hopefully, you know, overlapping would mean that you have the car, is, and then you can have another that is car is going, right? And so on. You could do that. And that just means that the index is incremented by 1. But here, there's nothing wrong with that. In fact, try it, make it, you know, make it work. But the way this is kind of working is the car is going, oops, sorry. The car is going really fast, right? So the index was here. Now, let's say the size was 3. And then offset. But given that code, the next offset will be there. Do you agree with that?
Yeah, Professor.
Excellent. I'm glad. Seems like this is making sense. So that's good. All right. So now, if you notice, we still need to get into some of the details of this, but we're in good, you know, we're in good, really good shape, I think. All right. So, and that's it. Notice that there's really just one session run in all of this, right? And all the code, that's one of the issues with NLP. A lot of the code sometimes in NLP problems are just about making the text into the vector. And then the last part, you know, this will be the last thing we cover, but this is where you generate the random sequences, the random stories. So I'm getting, you know, let's say, you know, you had built an AI with millions and millions and millions of stories of Star Wars, all the books that people write, the fiction, and then now you would have it generate its own story. So it's going to tell a story about a spaceship and, you know, Jedi and things like that, right? So, but unfortunately, it won't be grammatical because this doesn't take into account grammar, right? Now you could add that functionality, but it would have to be something additional. Anyway, we will come back to this in a second. And notice here, I just want to point out, notice here at some point, we run session run again, and we use the model to predict the words given sequences. And then we're going to print out our little story at the end, which will have a size of 64. All right. So that's basically it as far as the overview of it. So now let's do something so that we don't waste time, but also I can take a break from my throat there. I'm going to run the code in the next 10 minutes. Okay, I'm just going to run it. It takes a couple of minutes for it to run anyway. And then we can just, or you can ask questions. So let's take a 10-minute break of me lecturing from 1:20 to 1:30. Ask any questions that you have, and at the same time, I'm going to have the code running in the background, okay? All right, so I'm gonna switch over to the VM. Are you guys seeing my virtual machine now?
Yeah, Professor.
Okay, great. So I'm gonna navigate here. All right, that's the biggest it can get, it seems. Can you guys read this okay?
Yeah.
Okay, great. All right, so let me navigate. So I already downloaded the files. All right, so you can see there the story Belling the cat. That's a very small one. It's better to have a bigger story so you can try that Aesop's fables. I just think it takes a while on the VM for this kind of problem. So definitely run it on your physical machine. And then here's the code RNN NLP that, is pretty much the same code I've been talking about I downloaded it literally from the GitHub because I write this on my Mac. I should say that this will work on both Mac and Linux. I ran this and I usually write the code on my Mac and then I just put it on the GitHub and then I test it on this for the class. So okay, there it goes. As you can see there, what it's doing is every iteration, it takes a sequence of 3 words and it's showing the actual word because it knows that it's offset +3 plus the predicted word. So you can see that initially the words are not going to match. And so you could always use your accuracy, that accuracy function, you could use it here if you wanted to. And you could show the accuracy of this easily because you have the one-hot encoded vectors. So you could feed those. And in that way, you could actually have a measure of, so nowhere here did I use a metric, but you could easily add the evaluate function in there just by giving it the actual and the predicted, and it would in that way you can actually calculate the accuracy. So I leave that to you guys. At this point, basically signing you off on as deep learning ninjas, right? So I'm sure you can just modify that code. So you can see, I think I set it at 10,000 just because I didn't want to spend all that time training. When you run this on your own, increase it to 100,000 or so. Obviously, the more data you have, you probably want to use a GPU, things like that. All right, so you can see the stories are there, or not the story, the 3 word sequences. The first word is the real, and the last versus the last word, which is the predicted. Any questions?
Yeah, I was just trying to understand.
Can you speak up, Samendra? I can barely hear you.
I don't know, Professor, today what
Yeah, I'm sorry.
like,
I just want to hear you clearly.
Yeah. So I was just trying to understand how you are feeding your dictionary, an XTF and YTF. So in this case, you are basically looping everything within the main loop itself.
Looping everything within the main loop itself. What does that mean?
That is like the while in your main, the while loop.
Yeah.
So you are running 4 in there. That's what I mean. Like you're looping the words within your main loop and you are feeding it to your XTF and YTF.
That's right. We're going to do that, Sumendra. So we will do that. I'm just taking a 10-minute break right now.
Yeah, Professor, no problem. That's why you asked me.
We still have the second half. I've left the, getting into the heart of that.
Yep.
It'll,
Yeah, Professor, I will just keep
it'll
it
take
right.
a long time. Okay, so we'll get to it.
Yeah, no problem, Professor.
So, all right. So it finished processing. Do you see that? It did 10,000 iterations. You can see there. Enemy, comma, the cat. Oh, that's what it should be. It predicted it correctly. Period, some set this. See, that's correct. But then you see comma and some said, and your AI, your chatbot, whatever you want to call this, you're not very smart, said easily. Then you said that, but at, it predicted while. You see that? So that's why I was saying those are one-hot encoded vectors, last and while. So you can use the test function of the 4 core functions to just calculate accuracy easily with this one. Right. So now what happens here is you have to pick 3 words, type them in. It's going to take those 3 words as a sequence into your RNN, and it's going to predict the 4th word. So I'm just going to pick, I'm not going to type Mordor, right? So it's got to be a word from the dictionary. So I think if I type Mordor, actually, I put a try-catch in there, so hopefully it's not going to break mine. See, Mordor, words not in dictionary. So it needs to know what these words are, okay? So that's very important. So they need to be in the dictionary. So then I'm just going to pick 3 from what I'm seeing here. So I'm going to pick retire, comma, mouse. It knows those 3 words, and cat. And you will see that because I didn't train it that long, it starts to repeat. It'll do. That's why I think more text and more training would make this smarter. So notice that we said retire mouse cat, and then it wrote the story, retire mouse cat general. Well, with consists in slide. Treacherous spoke. That's actually funny. The propose had said it is easy to should of the cat said by escape last her applause. Enemy could thought is easy to should of the cat said by escape last applause. Enemy would thought is easy to should of the cat said by escape last. What that means, I'm not sure, but that's the beauty of NLP, of these things, right? So you can start to make this a little bit better and a little bit better and a little bit better, and adding things, and eventually you might get something that's at least makes you laugh. Okay. This is no different than our discussions we've had before about GANs, like how GANs could look at something and make it like a Picasso. This is kind of the same, right? We're learning, if I had written these stories, so notice it's talking about cats and it's talking about treacherous of some kind of a fantasy war type thing. And that's what the story, I think, was about. And so it starts to pick up those elements. Okay, and so that's the idea. All right. Are there any questions? Any questions, guys? We can try other things. Let's just do the. See? The is said by escape last her applause. Enemy could thought is easy to should of the cat said by escape applause, and so on. All right. So anyway, hopefully this makes sense. This is how we generate a story from RNNs. All right.
So Professor, for this code, it will always put the 3 words you import at the beginning, right?
For this code, you are literally concatenating predicted words one after the other. So We'll go over that. I mean, you can change it to however you want it. Here we just give it
Okay.
words, and that's the starting point so that it knows, you know, it makes sense, right? You know, you want to change it so you get different outputs every time. It's like a seed of words, and from there, it starts building this n-gram. What it's doing is it drops the last word, and then it just takes this one, and the predicted as a new n-gram. Then it drops that, takes this one, and the two new predicted, and so on. We'll see that in the code.
Professor, I checked this code at 50,000 epochs and it was working fine. And when I was like putting 3 words, it was predicting the whole sentence properly.
Okay. So what do you?
Yeah, at 50,000 epochs.
At what? Say that again.
At 50,000 epochs.
What about 50,000?
At 50,000. Yeah, like you use 10,000, right?
Yes.
So at 50,000, it was working fine. Like it was predicting everything good.
I see what you're saying. So the words are really accurate now in the prediction.
Yeah.
These words, they're all coming out as the same. That's what you mean?
Yeah.
Yeah, that's good. Great. Thanks for letting us know. As I said, I just didn't, you know, if I had run this at 50,000, I think it would still be running right now. And so
yeah.
I wanted to kind of cut it, but that's great. Great. All right. So now to address the questions that Sumendra had, which is getting into the meat of everything. Before I get to that, are there any other questions before I kill this VM and we go back to the GitHub? Or we could actually stay here as well. All right, so let's, let me stop it though. I'm gonna stop the program. All right, there we go. So now, let me switch over to the, all right, let me switch over to the whiteboard. All right, here we go. Are you guys seeing my whiteboard?
Yes, Professor.
All right, great. So let's then now get into the details of this. All right, so first I'm just gonna lay out some things. You probably, you know, the way that I do this that helps me is I usually like to like make a note of this because I want to like references. Whenever I'm looking at the code, I want to visualize the things, okay? So there's gonna be several things that you might want to write down. Okay, so, you know, this is the RNN. Okay, we have the content of it is some kind of a story. You know, the cat is ... sleeping. Oh, okay. So the content, the cat is sleeping. Right, and so on. So what we want to do is we want this to actually be a dictionary of words. That's going to be the very first thing. The cat is sleeping. So all we end up doing is we create a list of words, right? So we're going to take this and create a list of words, okay? There's going to be also, I should say, in the code, there's a list comprehension. All right, the list comprehension, and that list comprehension looks like, you know, Lisp comprehension, word for I in range lang of content for word in, oops, in, I'm just going to continue here, content I dot split. All right, so there's going to be a list comprehension like that in the code. I just want you to know that this list comprehension, if you read that, you might get confused. What I usually do is I just write it in my head as it would look in just a regular 4 nested loops. And the way you do that is then this would translate, this is just the first loop, this is the second loop, and this is what goes in the loop. So I would rewrite that as for I, and once you do this, it'll make perfect sense. Range, length, content, right? So that will just be the size of the document, how many words you have, not how many unique words, but just all the words. So if the appears 17 times, that's counted as 17. All right, so then you do this, and then, so that allows you to iterate through the document like an index, and then you do for word in content I, it's a square bracket, I dot split parentheses and then word. What this does, what this code does, and we'll see it in a print statement, is that it basically, when you get the document originally, it keeps phrases together. So it'll create like a phrase of 2 words, comma, a phrase of 3 words, comma, and you want to make sure that all of those are actually unique words. That's, you know, that's critical. That those are called the tokens, because the tokens can also be words, but they can also be, you know, the comma. The comma itself could be a parameter. Okay. All right. So then oh, I just learned that I can keep these. That's great. All right. So then you end up with now, you know, long ago, the mice had, you know, something, dot, dot, dot. You end up with a list like that. That's really what is happening there. All right, so then the next thing you do once you have this is you will need to create what is called a dictionary and a reverse dictionary. Now, a dictionary and a reverse dictionary, these are the 2 elements that are used extensively in NLP, okay, for NLP applications. So here they're being used in RNNs, but they're also going to be used in Word to Vec, okay? So when you start looking at that Word to Vec code that I posted, the one that Mitch will explain on next week on Tuesday during your presentations, you can literally, that code uses it as well. So both of these use it. So you need then to efficiently go from the story like this into these 2 dictionaries and reverse dictionaries, okay? So let's look at, now this is the thing that in my opinion, write this down, because as you're reading the code, it'll make it easier for you to understand what you're seeing if you have a picture of these 2 things. All right, so dictionary and reverse dictionary are 2 dictionaries you have in your Python code. They have the same information, they're just reversed. All right, and this is important. So the dictionary will look like this. The key is the word, and the index is the value. You see that? So you have something like that. Then the reverse dictionary is the opposite of that. You have the index, 1, and the output will be the. So you see, it's the exact same thing. So the is 1, and 1 is the. They're just reversed, okay? That's all it is. And it's a convenience so that you can quickly look up. So because remember that, let me just finish here. So said, remember that the algorithm predicts in an index, right? And so once you have the index, you can look it up in the reverse dictionary. Great. And then initially, when you're looking up a word, you have the word, and you want to get the index, and so you look in the dictionary. That's all it is. It's a convenience for you to look up things efficiently. Does this make sense, guys? All right, sounds like it makes sense. That's good. All right, so definitely write that down because that's helpful to understand. The next step is for us to think about the placeholders. We're gonna think about the placeholders. Notice I've used the exact same names we've used throughout the whole semester. Kept it consistent. So here, the tensor for XTF and the tensor for YTF will look like this. So this is none, which usually, if you look at your code, will just be batch size of 1. There's only a batch size of 1, and that's great because it simplifies our understanding of it. Then this is 3, right? So that means we kind of have this. Right, and then 1, 0 to 1. So ultimately, it looks like that. And for instance, this is the cat is. But really, and I just drew this as a cube to indicate that this could be a batch. So let me actually none, and then. And then this would be the batch size. In our case is 1, so there would just be 1 line in there. Okay, so that's what this looks like. And actually though, it doesn't look like the cat is. Instead, it's going to be whatever is in the dictionary. So if I go the is here is 1. And let's say that I have a cat over here, and cat is 18, let's say. All right, so I'm going to look up these indices. So the is 1, cat is 18. So really the is 1 because that's the, and this is 18, that's cat. Okay, and so on. So you're replacing the numbers with the word. So this would be is, let's just say is like 5. Okay, and that would be, three. And then this would be is. All right, and so that's how your XTF would look like basically. You're gonna learn to correlate these numbers to the outputs. Now on the other end, and this is no different if you look at it than MNIST. If you think about it, MNIST, you know, would be an image of 28 by 28, right? And so you would have numbers there like 255, 150, and you learn to correlate those images to a one-hot encoded vector from 0 to 10, right? That would be MNIST. In our case, we're going to learn to correlate these numbers here, to our labels, the YTF. And so that one's going to be, and that one's just two-dimensional from 0 to none. Again, the batch size, there's basically just one. And then, but the YTF here will be from 0 to vocab size. In the example on that blog spot document, the size there was like 112, I think. 112. That was the size there. I haven't looked at the vocab size for our example, but we can look at it. We can print it out easily and figure it out. Okay? Oops. You can easily figure it out, you know, just by doing length of vocab, or just actually vocab size will have a value. All right, and that's it. That's basically it. So then we have, then our model that our RNN that we're trying to build, it looks like this. We said that these are size 512, 512, 512, right? And then we are building an RNN like this. These are the outputs that we're ignoring, but so we're ignoring that one, but we want this one, which will be the fourth value that we predict. So in this case, it is going to be from 1 to vocab size, okay? And that just indicates, you know, what vector. Remember, these are one-hot encoded, right? So it's gonna be ... It's gonna be this is car. That vector represents car. Instead of a, you know, if you put the 1 over here, 0, 1, then this is gonna be cat, and so on. Okay, so that's, you know, that's really the idea. So then here in the inputs, it's gonna be 3, 8, or 18, 7, because that's our input vector, and that is the predicted output vector. All right, so that ultimately becomes our model. So now that we have this high-level picture of our approach, let's go ahead and run through the code. So hopefully these ideas will help us to get a better understanding of our code. So let's go ahead and let's go to the beginning, right? So we have to go back to the code now. So let me go back to the code. All right, so I'm going to go back to the code in the VM. All right, and I'm going to do. Can you guys see the virtual machine?
Yeah.
All right, good. So now let's go into the code. Okay. All right, so we have to start thinking. So we already went over this in a high overview of it. So now we have to think about the parameters, right? So the first one is we read the story, belling the cat. And we take read data, right? And it's going to produce trained data. So that's the first place where we can stop the code, is we can just do print training data. It's in this case, to view things, it's helpful to have a short story. And then here I'm just going to put like X raw input. X raw input. Okay, and so the first thing we're gonna visualize is training data. All right, so what's in it? It should just be the story. I'm gonna hit Control X, Y, run it. And you can see there, right? So it's just a story. Long ago, the mice had a general council to consider what measures they could take to outwit their common enemy, comma, the cat. All right, so it creates this list basically of these tokens, okay? So that's all that's happening there. Okay, so if you want to understand why we have, this is the list comprehension that I talked about, right? That word for in range length. So remember, I already explained how that works. And the reason why you do this is that when you first read the data here, if you look, I'm gonna do print content X raw input. Right, so if I do that, if I do this X raw input, you can see that initially that first read has phrases in it. So it'll look like, long ago, the mice had a general council, you know, it has different things. So you need to basically break that up into the individual words. You can see here, once we hit enter, we go from everything not being a token to basically tokenized like this, right? So that's really why we need that. So it just really does that simple split in there. So here, notice, you know, you read the data, then you strip, and then you go through the, you know, through everything, you're just cleaning it. And then after that, you have to iterate through everything and then grab every element that might be a phrase and split that again, right? By default, it'll split it by spaces. And then now you end up with the actual comma separated text, okay? Or just the text, the individual elements in that list. So that's pretty much that. So I think the only difficult part here is to visualize this list comprehension, but otherwise it's pretty straightforward. So then I can also get rid of this, right? And that just, no, Jesus. Computer. Oh man, I hope I didn't lose everything. What happened? Ph.D. 3098. Some program started on my computer and then the delete stayed in there. so let's hope that. All right, so that's the biggest it can get. Let's try this again.
Professor,
Yeah. Can
just
you tell
cancel
me?
this one and then
Huh?
just cancel this one. Open the file on gedit.
On what?
On gedit, the editor, graphical editor.
Edit? Hold on. Okay. And now what?
Try to see if it's modified or not.
Because what I want to go back to the nano though.
You want to go back to nano?
Yeah, I don't like working with this.
So there is no modification. So can you open the file again, Professor?
Close this one.
Yeah.
Because otherwise, I have to either download it again or. All right, I'm going to try this one last time. Nope.
Just give me a sec, Professor. File is being edited by mouse. Nano 2.5.3. You want to continue? When you hit yes, what does it say, Professor?
Yes. Oh, it opens. And
Okay.
no. Okay. Thanks, Sumendra.
No problem, Professor.
Yeah, all right. So, such a coincidence that when I was deleting, some programs started and it took over. All right. Anyway, so let's go.
Just continue, Professor. Do yes.
I have to do that every time, huh?
No, next time there is something running on the background, I guess.
But I killed everything on there, so I don't know.
And now just when you exit, just save it, Professor. Add something and save it.
Okay. All right. All right, so hopefully this works now. All right, let me run it actually so that I know that nothing is corrupted. All right, there we go. There we go. Okay, great. So I think it's working now. Thanks. All right, okay, so let's go back.
Just hit yes, Professor, and don't worry, it will be fine. I think there is something trying to like run the same.
Okay. All right, well, hopefully this will work. So, so now let's go back to where we were. So we covered this function. Okay, so I was deleting these things. And that's where it went nuts. So let me do that. And then also here. So I think this part should be clear, right? So at the end of the day, you take the story and you load it into training data as a list. So now you have a list of the individual tokens, where a comma is a token, the word cat is a token, the is a token, and so on. Now that takes us to this magical function build data set. It's actually, this does a lot of the heavy lifting when you're dealing with NLP, whether it's RNNs or whether it's word Tyvek, this function is central to that. Okay, so you guys see the function, right? Build data set. Yeah. All right. So what happens here, notice here, this is where you calculate the vocab size. All right. And you do that by measuring the length of dictionary. So let's take a look at that one. I'm curious to see what the vocab size is. I never actually looked at it because that's going to be your dimension of your hidden layers. Now, of your layers, really. So you want to think about this a little bit. Get that value, compare it to the size of hidden dimension, and assess. So here, let's add X raw input. So X raw input. All right, we're going to run this code now. And oh, there we go. So it's actually 112. That's what it ends up being, 112 for that particular story. So it matches what's in that blog that we looked at. All right, so now that we understand that, we can remove this. All right, we don't have all this text there. Okay, so really the trick is dictionary and reverse dictionary. So I already gave you a picture of what these look like. So notice it takes just a story, which is in a list format, and it builds the data set. So now let's go to the build data set. Notice that this takes the words here, right? So this takes the words, runs them into build data set. And now the very first thing you do is you run from collections, you run the counter of words, and then you select the most common. So that's really, that one line performs a frequency count. So you don't have to do it, right? This performs a frequency count of the words. So it literally looks at all the frequency count. It looks at all the words, and it's going to list all the words, and it's going to say, oh, I saw the word the 150 times. I saw the word so-and-so many times. You know, so it shows all of them. Okay? Does that make sense, guys? And that object will be in count. Then you create the dictionary, and then now you're going to iterate through count. Okay? So you're going to iterate through count, and you're going to say for word and something else, because there's a tuple in there, in count, and you're iterating through all the words in there, okay? And then you assign them to the dictionary. So you assign the word, right, cat, and then you're going to give it the index of it, okay, the index of it. So the way this is done is actually, if you print dictionary, that's really where it'll become more obvious. So I'm going to do print dictionary. Okay, and then I'm going to do X raw input. Right, and now we can see what's going to happen, the behavior. So let's go ahead. So I'm going to ask you this question. Which word do you think will be the most frequent in this text? What word would you say will be the most frequent here? Anyone?
Cat.
Cat? Is that the most frequent? Let's see.
That's what you are talking about all the time. The cat. The cat.
Well, yeah, I like cats. That's, that doesn't mean it's the most frequent. So let's see. So
Might be the, I guess.
yeah, the. It's actually the, because it is the most frequent word, right? You know, that's what it is. So let's run it. And you see, it's actually comma. Comma is the most frequent word. So it's going to be, so what the dictionary, what that frequency count does is it calculates the most frequent words and it sorts them in descending order from the most frequent to the least frequent. So initially the very first one is the comma. And that's why, because it grabs it first, right? It's going to make that the very first one in the dictionary, okay? Then the gets index 1 because it's the next most frequent. You see that? It's just assigning, right now, these are not the counts that it's putting there. Instead, it's assigning indices based on the frequency. All right, so the most frequent words go first. All right, that's how it works. You see that? Period is 2, and is 3, 2 is 4, set is 5, 2 is, a is 6, could is 7, that is 8, 9 is some, 10 is we, 11 is he, and so on. Does this make sense? So that's the dictionary. You're basically assigning a word and an index. That's all it is. But it all comes from the logic of finding the most frequent 112 words, and then there iterating and creating this. So let's go back to the code. Oh, it's opening now. All right, so let's go back, and you can see here then, you know, I do the frequency count, then I iterate through the frequency count, given the most frequent words. So the very first one was period, right? And I'm going to look at the size of the dictionary. So initially, the very first word, the size of the dictionary is 0. That's why it gets 0. Then I add it. The next word, then the next most frequent word will be 1, because the size of the dictionary is 1. And then I add the word, and so on and so on. Okay, we can see that again. And you can see it there, right? So convince yourself that the most frequent is 0, then the next frequent is 1, then the next frequent is 2, and so on. All right, so that should be clear, I think. So once we, so notice that that little code, this little function is extremely powerful. All right, once we do this, then we have, we finish the dictionary, right? And notice the next step is to take the original dictionary, and now we're going to flip it. So we use the SIF function. The SIF function is a way that, you know, a dictionary has keys and values, right? So now we're going to make, whereas before we had keys and values, now we have values as keys and keys as values. So we're just flipping it. And that is called a reverse dictionary. So once we're done, we print out dictionary and reverse dictionary. Okay, so I'm going to delete these things. Okay, so now if we go down here, if you'd like, you can print out, just to convince yourself, you can print dictionary, and you can print reverse dictionary. Okay, and that way we can take a look at them. Let me do X all inputs. We can pause it. All right, so now let's go ahead and do that. So I'm going to do Control X, Y, enter, run both of these, and you can see it there, right? So this should be dictionary. The is 1, enemy is 21, whatever. And then if you look at this one, it's inverted. So now, enemy there is the word, and it's 22. No, 21 is enemy, and enemy is 21. So they're just inverted. Okay, and that just allows you to do really fast and efficient lookups when you're calculating your values. Okay, and like I said, Tyvek works a little bit like this as well. It'll have a dictionary and a reverse dictionary. So it's the same principle. Okay, so now let's get rid of this. And that's it. If you look at this part, just those two simple functions allow you to now have the features, basically. Now you have these dictionaries, these reverse dictionaries, and you're ready now to do everything else. So notice that's it as far as getting the text ready for you to use, right? So you do that there. And then the next part where you have to manipulate the data will be in the main loop. So remember that, okay? So now you need to remember how these, that's why I drew these and I said, you know, remember how these looked, because now we're going to go to the next section. Okay, so we did build data set, did dictionary, we have dictionary, reverse dictionary, we have vocab size. Now notice here, this is just a print stat metrics, this is just plot metric per epoch. Nothing has changed there. We will look at this one also, and actually this one we can look at right now. This function is RNN NLP. Notice it'll be very similar to what we had last week, right? Exactly. Notice that we have the weights and the bias. And remember that this weight and bias is for the connections between the hidden layer and the outputs, okay? So for instance, here you can see TF variable, TF random normal, and the sizes are vocab size. Notice here, vocab size, so that's 112. And weight is from n hidden, which is 512, to vocab size, which is 112. So remember that this is exactly the connections from the hidden layer to the output layer. So let me do this. I know this is something we did last week, but we can do it again. So this is defining basically, you know, those W's, right? That W, which is the connection between 512 and this one, which vocab size is 112. Okay? And the bias, remember that the bias is always added to the output. Bias will be also, you know, 112, okay, or vocab size. Okay, so that's what we're defining there, the weight and the bias, and they relate to this segment of the recurrent neural network. All right, so let's go back to code. Okay, so now I'm going to screen. Okay, so nothing changed here from last week. Okay, then over here, so you can look at that video, RNNs, and it's very similar. Notice here the input is the X, so it's gonna be the sequence of 3. Notice here in the we have a reshape function again, reshape to 1 by an input. Okay, remember that the -1 just infers the batch size. Our batch sizes, as you will see in this example, are 1. We're not feeding, let's say, 5 or 10 or 100 sequences of 3. We're just feeding 1 at a time. And so you can see that, you reshape 1 by an input, okay? 1 by and then you give it the data X. Then in this case, now you're going to do the split. Remember that split, that is something that the RNN needs, all right? So you need to do that split there, and you generate an n input element sequence of inputs, okay? So for instance, you would have had a general, right? And so that's equivalent to having 2633. Those are the inputs that we have. So here, let's do a little exercise here. So we have to, let's try, so I gave you some code last week to look at the shape of tensors, right? That was in the RNN. Let's try that. So let's see. So it's gonna be print see if this works. Raw input. Oh, not there. So print. And I'm going to do session dot run tf dot shape of x. Okay, so we're going to try that. So when something is in a function, that's the only thing I don't remember if I have to pass the session in here. So let's try this. So I'm going to do x equal raw input. This is certainly a very useful function to use. So now, let's run that, see what happens. Yeah, global name session is not defined. It's not, so let me try. The problem is that the session is I have to pass it through, I think. So I declare my session here. Here. So let's see if I pass it to this. All right, so let's try that again. Yeah, so it's not liking that. So it didn't like the session in there. Possibly because it hasn't been.
Professor, I guess you can define a init as a global variable over there when you initialize.
Where?
Yeah, over there when you initialize this session, you can define it as an
A global variables instead of initialize whole variables?
yeah, just try it once. Like,
And that does it?
and hopefully it's supposed to pass.
Init equal tf dot, what is it? Initialize as global, initialize?
TF global underscore variables initializer.
TF dot?
Global underscore variables underscore
Hold on.
initializer.
Variables underscore initializer?
Yeah, it's a function.
Initializer, okay.
Yeah.
And then do I need to pass the session or not?
You already call it on a session on the down, right? So eventually it will pass.
So you're saying in the function it does not need to be there anymore?
Yeah, I think so. You don't need to define it anymore. I suppose like now it.
Okay, so remove this then.
Yeah.
Okay. And then here. Hopefully that'll work. All right, so let's try it again. Global set is not defined.
No, it's not working, I guess.
Yeah, it didn't work. So there's Gotta be. I don't want to waste too much time on this, but I wanted to print those. And the problem is they would print easily if they were outside. It's just passing this. So the other way, I guess, that we could do this is, let me try passing the thing. Just try that. Okay. Nope. All right, I have an idea. So let's do this. Forget about the session inside. Forget about this in there. Instead, I'm going to create x1 equal x, and I'm going to create x2 equal this x. All right, so those two variables should maintain the dimensions. So now whenever I run this, I'll also print out x1 comma x2. So if I do that, get rid of that. And we go back to what I had. Problem is, when I call output now, there's comma x1, comma x2. So let's try that. So now, let's see if I can get the shape. So it would be somewhere down here. Somewhere down here, I call train up, I called output. And I can call here x1, comma x2, which then I have to capture here, x11, comma x22, comma, and then let's see. So I'm just going to try this. If this doesn't work, we're going to go back. And then so here it would be session print session.run, and then it's going to be tf.shape x1. Oops. And then this would be x raw input, like that. All right, so let's try that. Where's the error here? Line 2. Yeah, it's in the shape. Oh, that's the wrong name, correct? That was the wrong name. Should have been X11. Okay, let's try it again. All right, there we go. Okay, so X13. That's what it printed. Is that correct? It should be, right? Because it's one sample of size three features, right? So, you know, if we go back to the code, over here, we look at the inference function, and in the inference function, we do TF reshape X. Well, our X was just one sequence, so we infer the none as being 1, and then this is 3. So it's 1. So the shape of it from when we do the tensor analysis is 3. Does that make sense, guys? Yeah?
Yes, Professor.
Huh? Say that again? Can you speak up? I can't hear you.
Yeah, Professor. So initially,
So I'm just, yeah, go ahead.
so initially our input was in a dictionary, right, Professor?
Our input here in X, we're going to see that in a second, so that's where I'm going. But just imagine, regardless of what this input was, we reshape it to 1 and 3. Because there's no batches. If we had a batch of 10, then it would have been 10 and 3 or something. But we don't have batches, okay?
Okay.
Yeah?
Mm-hmm.
All right, so now let's take a look at the X2, right? We want to see, because we want to see what happens when we do the split. So this is going to take X 3 and 1, right? And it's going to do that type of a split. So now let's go ahead and take a look at that. So we need to do X22 as well. Here, pretty much the same thing. Print. The values here don't really matter, is what I'm trying to show you. It's really just the dimensions of the tensor that we want to analyze. TF shape, and then we do X22. So hopefully that will work. This is after the split. I didn't like this one. Well, it got X22, which it says down here, got shape 3, 1, and 1, but wanted 3. What wanted 3?
God.
Not sure why that's giving an error, because it should just give us the shape of the object, right? And notice that it converts it into this, right? So the 3, so it just literally changes the shape of it to be 3, 1, and 1, which is, you know, one batch of one depth, and there's 3 values in there. But this is the shape that you get. I'm not sure actually why this is erroring out. It makes no sense to me.
So what's supposed to be the shape, Professor? Is still the 2-dimensional?
Say that again?
Is it still the 2-dimensional?
No, this is really important, because if you look at this, it says here this is what it got, right? So I was expecting actually to get this value, but just like we got it here. I'm not sure why this gave me an error, because it should just be a tensor and I take its shape. Unless it's a list, and that's why it gave me an error. You know what I mean? It could be that actually, Sumendra. Then. So there's a way to prove that. This one is a tensor and it worked, and it gave me shape 1 and 3. This one has a shape like this, but it didn't like it. So let me try one more thing, which is because you know that split by definition, it creates a list. And so I wonder if all I have to do is sort of print the NumPy shape, which I don't remember. Let me try this. So I'm going to comment that out. And I'm just going to do print x22.shape. I think that's how you do it in NumPy. Can't remember. Nope. Yeah, list object has no attribute shape. So notice it's a list object. So what we need is, if anyone can tell me how to get the shape of a list, that would be great.
So, Professor, do you need that parenthesis
The parentheses?
after the shape?
Yeah, I'm going to take that out, and I'm also just going to print x22. You know, let's see what that gives us. But I'm almost convinced that the reason why it gave me an error is that that split creates a list. It's not a tensor anymore, and that's why the tf.shape didn't work. So I'm hoping that's the case. So let's try this again. Oops. No, it has no attribute shape.
That means
What is the shape of this?
I think it is still not a NumPy array.
Huh?
I think it is still not a NumPy array.
Yeah, hold on. I'm going to look this up on Google here. So shape of list. Yeah, so there's no built-in function, it seems, for this. All right, I know we're running out of time, and unfortunately, I really wanted to see that shape. We tried this np.shape. Let me try that. I just don't remember right now what it.
You forget one parenthesis, Professor.
Huh?
You just forget the parenthesis.
I did what?
You forgot, so there is an error in the code. You forgot the parenthesis. Yeah. And
Oh, I'm missing a parentheses.
yeah. There you go.
There we go. Wow. The seat of our pants. Okay, so there we go. So notice that we go from 1 and 3, a tensor, and the split function creates this list of 3 by 1 by 1. Okay, so that's how we give the data. Okay, so those are the dimensions that we end up with, and that's the way RNNs work. You know, it's not like, if you've noticed, we did the transpose, reshape, and split in the MNIST example, and now here we didn't need the transpose because we didn't need to change the shape like that, but we still needed the reshape and we still needed the split. All right, so the definition of that split, if you look it up, is that it creates a list. All right, and this is the shape that it gets. So if you remember that analogy that I gave you, I think it's the best, right? It's like you load the machine gun from below, right? You put in like the clip from below, not from the top. And so think of that as the RNN just needs the data to be in this format. Is this clear?
Yes, Professor.
Yes?
Yeah.
Okay, great. All right. So you can play around with this, at least we saw how to view the shapes. So I encourage you now, go back to MNIST, take a look at it as well. And so this, whenever you're doing your problem, this will help you to figure out how to feed the data. Okay, so we still have a little bit of time, so I think I can finish this. So I'm glad we were able to get that solved. So now let's go back to this part here. So we were in the inference function, actually. So we were in the inference function. So everything else should be easy now. So notice we created the W and the bias. I already talked about that. We reshaped the X. We already saw the shapes of it. Then we do the split, right? And that, is basically taking our words, right? 2633, and we feed it as a list of values and then of vectors, basically. And then notice here we create the RNN cell. So that's just RNN basic LSTM cell of size and hidden, which is 512. Now notice here, I left this commented out, but actually you can create RNN cells of more than one layer, right? So that's like saying, I have an input and an output, but in between, I don't necessarily just have to have one layer. I can have 2 or 3. So for instance, here, this is one layer LSTM, but notice if you want to try a multi-layer, you try RNN, multi-RNN cell, RNN basic LSTM cell and hidden, and then again, RNN basic LSTM cell and hidden. So now you have 2 layers. And so it's just like with, now it's deep, right? So now it's an RNN that's also very deep in these layers over here and the RNN cells. So what I would say is, comment this one out and uncomment this one and try your model with multiple layers and see how it does, okay? Then finally, the last part over here, we run the RNN, static RNN here. We give it the RNN model cell and we give it the data. This is the easy part, right? We give it the X, so it takes care of everything. And then it gives you the outputs and the states, So remember that this part, if I go to the share the screen here, whiteboard, and I do this, right? So that's, in that output section where you have the inputs, and the output, you're getting this, but you still need to do the matmul between the weights and the biases, okay? So that's what you're getting with the outputs over there, right? And so you can see that if we go back to our virtual machine, all right, so if we go back to our virtual machine over here, right, we get outputs and states. We're not using states right now, although there's valuable information there. We're only using outputs. We give it the RNN cell. We give it the X. Are you guys seeing my VM? Yeah?
Yeah, Professor.
Okay, great. And then we perform with that last output and the weights matrix and the bias, we perform a matmul, and that gives us our RNN outputs. we have this RNN output over here, right? And this was just the X1 and X2 that I added. So that's basically your inference function right there, okay? We already talked about all of this. We already talked about all of this. We already talked about all of that. I just noticed I had a typo here. See, Sumendra? I wonder if that's what caused it to error out. Maybe that would have worked. All right, so then the last part that I need to cover is this main loop. Okay, so this is important, right? So we already understand. Now imagine that you have three elements. You have the dictionary, reverse dictionary. I defined both of those things already. And I have the story, right? And I have the offset, which is the index. So I have the story. So what do? I need, first of all, the three words that are the inputs to the model, right? The cat is. So how do I do that? I do a list comprehension. And I'm going to do for I in range of offset, which is where it currently is. Let's say it's in position 15. And I look until 15 plus 3, because I'm going to look at the next four words, right? Which is going to be the two words plus the predicted one. So I do that. I get those indices. And then I go into the training data, which the training data is the story as a list. And I get those words, right? So I get the cat is sleeping. I get those. They are made into a string, right? And notice that as I do that, I take the words, the, look it up in the dictionary, and now I get the number, the IDs. So if I got the cat is, I'm going to end up with, from looking up the dictionary, I'm going to end up with 3, 17, 5. And that's my list of symbols. Is that clear? All right, and I get that, and then I take symbols, right, and I make it into a NumPy array, because your TensorFlow is going to need NumPy array here, and then I just reshape it, and it has to. This is where you reshape it so it matches XTF. Okay, so if you remember, XTF is none by 3 by 1, right? None by 3 by 1, and so we reshape it into exactly that. And so now I'm going to have that cat is, which is going to be 5, 17, 9. Okay? And that's symbols in key. That's my input to the feed dictionary. So if I go down here now, notice that we call all of these variables. In the session run, we call train op, eval op, cost, output, no one hot, and even the X1 and the X2. And notice here that those are the parameters we call, and then we just give it the feed dictionary. In the feed dictionary, notice, I just give it symbols in keys into XTF, because symbols in keys is already in the appropriate shape that the XTF placeholder is expecting. Is this clear? This clear? Can I move on?
Yeah, I think so, Professor.
Again, you have an offset, you know the position, and then you just take whatever that offset is, 37. So 37, 38, 39, and 40. Those are the terms that you want, right? And so words from training data. Training data is your story. So 37, 38, 39, that's going to be the is. You get each one of those, you're iterating through them in this list comprehension. You make it into a string, and then you look up those things in the dictionary. So the idea is that you're going to exchange the cat is for 7, 18, and 5. And that gives you your symbols in keys. And then here, you just make it to a NumPy array, and you reshape it to fit the placeholder. Okay? So once you've done that, you can feed it into the feed dictionary down here. XDF symbols in keys.
Professor, I have a question. How big is the vocabulary size?
112.
Oh, thank you.
All right, then over here, the next step is this part, and this is the label. So whereas this is the sequence of words in the RNN, this is now the label associated with it. So if you look, we have, we create basically np.zeros is a NumPy array of size vocab size. So what is this? It's basically a vector of size 112 where all the values are floats and they're zeros. You see that? So we created the one-hot encoded vector, but it has all zeros. Then one of those 112 needs to be a 1, and that's what's happening here. So if you look, I even wrote this down over here. Basically, we need to find which word, so word 37, which is cat. So in this vector, 37 gets a 1.0, everything else is a 0. And that's what happens here. So I go to train data. Again, I know what offset is, right? I know what offset is. You know, it was, let's say, 55. So the predicted word has to be 55, well, you know, 55, then 56, 57 are the sequence. So 58 is the actual predicted word. You guys see that? Again, in the trained data, this is the data, the story, and here my offset is 55. So that's the start of the sequence of 3. That cat is. So that is 55. Cat is 56. Is 57. Sleeping is 58. And so it's going to be 55 plus 3, 58. Grab sleeping from training data. And once again, I have the word sleeping. I make it into a string. Look it up in the dictionary over here. And that tells me that sleeping is actually the word 101 in the dictionary. And so now I take the vector of zeros, and for the index 101, I assign a 1, which is what's happening here. And so that's why this is equivalent to saying something like vector 37 equal 1. Okay? And once I've created the one-hot encoded vector, I do the same thing. I just reshape it. So I take symbols out one-hot and, you know, basically reshape it into a 1 minus 1, which is the same shape. Okay? But I made it into a NumPy array is really, you know, NP reshaped it. It was a NumPy, I just reshaped it. Okay? And again, we don't have time, unfortunately, but you can print out the dimensions before and after, and that should give you a little bit of insight of how it ends up being. We're just inferring that we got 1 row and 112 columns here, basically, for that tensor. And that becomes symbols output one-hot. So it is one-hot encoded. At that point, it's also ready for YTF. So you can see that symbols out one-hot is assigned to YTF. And that's it. At this point, you're able to feed the training data and the labels into our model. Then we did all of this reshaping. And then finally, you're done. Once you now notice that in this session run, we don't just do the training, but we also run output as well. And in particular, output no one-hot. And the idea is that we are able to both run, given that we have a sequence and a label, we are able to run with that sequence. We run that same sequence to train it, and then we take that sequence and we run it with the predicted model to give us the predicted word. So when we get the predicted word, we have that in pred word over here. Pred one-hot is the one-hot encoded version. I already discussed pred word, which is, you know, I use argmax to extract the index. So now I have the predicted word, right? So if we go back to the example, the cat is, maybe the real word was the cat is sleeping, but here we say the cat is bird. Okay, so it predicted the wrong thing. we want to view it, and this code should be pretty straightforward. Again, you know the offset, and you know size of n input, so you can once again do the same thing for I in range offset to offset plus 1. So you iterate, let's say you're at offset 65, so then 65, 66, 67, 68. You're going to grab those 3 words. You grab them from training data, right? You have the words now, and you have the sequence. So the first thing we can do is just print the test sequence. So we print the cat is. Then we take offset plus input is going to give you the actual word after a sequence of 3. So we get it from training data. That would be the test actual after sequence. So that would be the cat is sleeping. So the word sleeping would be this, the actual. And then we take the predicted word, which is what we got from the model over here, from the session run. We take that pred word, int pred word, feed that into the reverse dictionary, and that gives us the predicted word, so bird. So we end up with, iteration whatever, the cat is sleeping here, and then here bird. So that's where you saw how it was predicting all of those words in the model. And that's it. That concludes, I'm only 3 minutes over, right? And that concludes the explanation of the RNN model. So, I'm recording this video, so hopefully if I went a little bit too fast with some of these things, at least, look back at it, stop it, maybe think about it, but hopefully it should click for you. Okay, the last part of this is I leave this as an exercise for you guys, but this is once you want to generate your short stories. Basically, you do this in an infinite loop. You pick a set of 3 words, right? You split them, and then you do the same thing. You take the 3 words again here, right? And you extract you look them up in the dictionary, right? The IDs, and then that's going to be your inputs, right? So you're going to reshape them, and then you just run the session run. So the session run takes only the inputs. XTF is keys. So the cat is, and again, it's just going to give you the predicted word because you only run output no one hot. And then once you get the predicted value, you put it, you basically add it to your sentence, and now you have the final output. And then for the next iteration, the new sequence will be the previous sequence, but minus the first word. So if you had the cat is going, then the next will be cat is going, and then you predicted going down, so it's going to be is going down, and so on. Right? So certainly play with this code. I know I'm kind of rushing through this one, but you basically, I'm sure can just print statements and figure out the logic of it. All right, so unfortunately we are out of time, but I do believe I've gone over all the code. So this concludes our discussion of recurrent neural networks. Are there any questions? Are there any questions, guys?
Professor, I have one question actually. So
Yeah, go ahead.
when we are feeding YTF as a symbol 1 hot, right? So dear, are we using the text itself as a label for a 1 hot coding or the key from the dictionary?
You're using the numbers, not the words. Is that your question?
Yeah, the index, right, Professor?
You do not, yeah, you cannot feed words, actual words, to a deep learning algorithm. So this one here gives you, so the keys is the thing you're concerned about, correct?
Yeah.
Okay, so let me print this. So print symbols. So that's why you have the dictionary and the reverse dictionary, okay?
Mhm.
So symbols in keys, okay? So you take the words from the story because you know where you are in the story by the offset. That's, you know, I can't stress that enough. But you know, I can't stress that enough, but you look up the cat is, those three words in the dictionary, and it's gonna give you these numbers over here.
Okay.
You see that? 131 and 19. That is your input to the, that's your input to the RNN, not the words, but the equivalent index in the dictionary.
And these index are used as a label, and which is one hot coded, right, Professor?
These, yeah, yes, you're right. So 31 just means the word cat. So you could write that as 31, which is how we feed it as the input, but you can also write that as a one-hot encoded vector of, you know, from 0 to 112, and index 31 has a 1 and everything else is a 0. In fact, the inputs could also have been one-hot encoded, as you know. You could have done that, it just would have been a different logic. It's up to you how you do it, but you'd have to make the dimensions correct. You see that?
Mm-hmm. I got it.
You got it?
Yeah, Professor.
Perfect. All right, I'm glad. So, so this concludes our discussion for today. Remember, please, next week presentation. So all of you need to present your projects in the class. And that's it. So this concludes, you know, the lectures. As I said, Mitch is going to present on Word Tyvek. I kind of discussed Word Tyvek at the beginning today, and you guys, you know, saw that. So certainly try that code. The only topic that unfortunately I was not able to cover is reinforcement learning. So, you know, we just ran out of time, unfortunately. But if you do independent studies with me, we can always, you know, tackle that topic that way. Okay. All right. So
Professor, when is the exam week?
exam is, so you can look this up. But let's see. So if you go to, PNW final exam schedule, right? And then you're going to look up in there spring 2020. And our class meets on Tuesday, and it meets at noon, at 12 o'clock. So if you have a class on Tuesday at noon, it means that your exam is going to be on Tuesday from 12:30 to 2:30, and that's going to be on May 5th.
Okay.
All right?
Yep.
Okay.
And Professor, one more thing.
Yes.
For the project, we have to submit it like we usually submit the homework on the Blackboard.
You have to submit your project on Blackboard, you have to present, and you have to do the demo.
Okay. But the pattern will be same like homework, like we used to put in the Word file and the code and the data set and all the things, right?
Say that again, sorry.
I'm saying the format will be the same as the format of the homework, right?
Yeah, you submit a report.
Okay.
Any other questions? All right, guys, so if there's no other questions, again, please don't forget your presentations next week and the exam 2 weeks from today. So we'll stop here for today. And if you have any additional questions, either email me or office hours on Thursday. All right. Otherwise, you know, we're done for today, and I'll see you guys next week.
Okay.